When we studied the Jordan-Holder decomposition, we saw how modules that satisfy the ascending chain condition and the descending chain condition are built up in a certain way of modules of a specific kind called simple modules. These are modules which do not admit non-trivial proper submodules. There's another way of breaking up modules into building blocks, and that is into indecomposable modules. So in this lecture, I'm going to introduce to you the notion of an indecomposable module. So let R be any ring, M an R module. Okay, so we say that M is equal to M1 direct sum M2 if the following conditions are satisfied. Firstly, M1, M2 are submodules of R. In other words, they are abelian subgroups of the additive group of M, and they are closed under the operations from R. Okay, when I say R module here, I'm talking about a left R module. Then the second condition is that M is equal to M1 plus M2 as an abelian group. So what this means is that for every M in M, there exists M1 in M1, M2 in M2, such that M is equal to M1 plus M2. Every element of M can be written as a sum of an element of M1 and an element of M2. And the third condition is that M1 intersect M2 is the trivial module. And this is equivalent to saying that the decomposition M equals M1 plus M2 is unique. Let me explain why, since it's quite simple. Suppose we have M1 plus M2 is equal to M1 prime plus M2 prime, then this implies that M1 minus M1 prime is equal to M2 prime minus M2. Now this is in M1 because M1 and M1 prime are in M1. This is in M2 because M2 and M2 prime are in M2. So both these things belong to M1 intersect M2, but that consists of only the element of 0, which means that M1 is equal to M1 prime and M2 is equal to M2 prime. So this third condition means that the decomposition of M as a sum of elements from M1 and M2 is unique. And now we can define an indecomposable module. M is said to be indecomposable if whenever M is written as M1 direct sum M2, then either M1 is 0 or M2 is 0. Okay, every submodule can be written, M can be written as 0 plus M or M plus 0. But an indecomposable module is one that cannot be broken up into two non-trivial summands. For example, every simple module is indecomposable. Why is that? Well, if we write M as M1 direct sum M2, where M1 and M2 are both non-trivial, then both M1 and M2 are non-trivial proper submodules of M, and so M cannot be simple if it is not indecomposable. Now there's a nice way of thinking about direct sum decompositions which will be very useful in the next few lectures. So let me introduce that. And this is sort of the beginnings of the calculus of projections. So now suppose, so maybe I'll just call this the calculus of projections. So suppose we have M equals M1 plus M2. Okay, then what you do is define Pi from M to M as follows. So if you have an element M, then you can write it as M1 plus M2 in a unique way with M1 in M1, M2 in M2. And so you just take P1 of M to be M1 and P2 of M to be M2. Then what we have are the following properties of these things. So you have the identity map of M. It goes from M to M. This is equal to P1 plus P2. That's easy to see because M is M1 plus M2. So P1M plus P2M is actually equal to M, which is the identity map applied to M. The second property is that Pi squared is equal to Pi for I equals 1, 2. Each of these Pi's is its own square because once you apply P1 of M, you already get M1, and then when you apply P1 of M to an element of M1, it will be written as M1 plus 0, and so it is itself. So the point is that Pi of M is equal to M if M is already in Mi, and because of that Pi squared is Pi. And the third property is that P1 P2 is equal to P2 P1 is equal to 0, and this is because P1 of M is equal to 0 if M belongs to M2, and P2 of M is equal to 0 if M belongs to M1. So both these are easy to check from the definition. And now if you take P2, you take any element M and then apply P2 to it, you end up in M2, and then when you apply P1, you will get 0. And most importantly, P1 and P2 are R-module endomorphisms. What is the meaning of end Rm? This is defined to be the set of all R-module homomorphisms from M to M. This end Rm itself forms a ring. Addition is pointwise addition, and multiplication in this ring is composition of homomorphisms. If you have two homomorphisms from M to M, you can compose them with each other in any order that you like. So in some sense, all these things which we've written are happening inside this ring end Rm. Now the fact that P1 and P2 are in end Rm rests on the condition that M1 and M2 are submodules of M. I leave it as an exercise to you to check that because M1 and M2 are submodules of M, P1 and P2 are R-module homomorphisms. As an example, as an application of this calculus of projections, let me show you a module that is not simple but is indecomposable. Z as a Z module is not simple. We know that right? There are lots of submodules of Z. For example, multiples of any integer n form a submodule of Z, but it is indecomposable. And one way to see this is to use the calculus of projections. So firstly, let's compute end Z Z. Well, it turns out that if you have a Z module homomorphism from Z to Z, it's completely determined by the image of the unit of Z, namely the integer 1. If you know where 1 goes, then you know where everyone else goes. And so but 1 can go to any integer, and so end ZZ is isomorphic to Z. And further, you can check that the operation of composition corresponds to multiplication of integers, and the operation of pointwise addition, well, that's more obvious, corresponds to addition of integers. So as a ring, end ZZ is isomorphic to Z. So if Z is M1 plus M2, then what we would have is 1 in Z, that's the identity map from Z to Z, would be equal to P1 plus P2, where P1 squared is 1, P2 squared is 1, P1 P2 is 0, P2 P1 is 0. Of course, this follows because Z here is a commutative ring. But these equations only mean that one of P1 is 1 and the other is 0. So the set P1 P2 is equal to the set 1 0, which means that either M1 is 0 or M2 is 0. Which is the definition of indecomposability. Let's look at another example. Z mod P to the kz is an indecomposable Z module. So again, you show, just as before, that the endomorphism ring of Z mod P to the kz is isomorphic as a ring to Z mod P to the kz. And so if Z mod P to the kz had a decomposition M1 plus M2, and we call P1 and P2 the corresponding projection operators, then we would have 1 equals P1 plus P2 in Z mod P to the kz, where P1 squared is equal to P1 and P2 squared is equal to P1. Again, you can check that the only elements in Z mod P to the kz that are equal to their squares are 1 and 0. Just as before, this needs a little check. And so either M1 equals 0 or M2 equals 0. And so Z mod P to the kz is indecomposable. However, if you take, for example, Z mod 6Z, then this, by the Chinese remainder theorem, is isomorphic to Z mod 3Z direct sum Z mod 2Z as a Z module, and therefore it is not indecomposable. In fact, in general, Z mod NZ is indecomposable if and only if n is a prime power.